Welcome back and to the next lecture of energy conservation and waste heat recovery. So, today we will continue our discussion on energy storage, especially on the mechanical energy storage technologies, and as told in the last class, today we start our discussion on flywheels. Okay. So, what is a flywheel? To start, what I am going to do is I am just going to play a video over here and from this link, and then we will talk about it. This kind of in a nutshell captures how a flywheel works, and then we will talk about what a flywheel is.
Energy storage flywheels have very high performance and work on simple principles. To understand their operation, it is best to start with the electric motor generator. An electric motor and generator are really the same machine running in opposite directions. When you put electrical energy into a motor generator, it turns into mechanical energy on the spinning shaft. That's a motor. When you put mechanical energy into the motor generator by spinning the shaft, you can draw electrical energy back out. That's a generator. For an energy storage flywheel, we hook a motor generator up to a wheel. When we put electrical energy into the motor generator, it accelerates the wheel, storing that energy as momentum on the wheel. When we want our electricity back, we let the momentum of the spinning wheel drive the motor generator, regenerating our electricity and slowing the wheel. Because we run our flywheel in a vacuum and on very good bearings, we don't lose much energy over time. Velkis has invented a new way to make energy storage flywheels at very low cost.
Alright, so that video nicely captured how a flywheel works. So, as you can see, a flywheel, it is a rotating member as we know, and with a shaft which can be rotated by using external energy, and then the kinetic energy, the energy that is stored in the form of kinetic energy, can be retrieved later. So that and when it is connected to a generator and it rotates the generator. So, that is what we saw there. So, flywheel over here, as the schematic is showing, it is a rotating device, and what is happening is it is connected to a motor generator set. Okay, it is the same machine. The way you operate it, it can act as both as a motor and a generator. When we actually supply external energy in the form of electricity, it acts as a motor, and that imparts energy to the flywheel, and the flywheel starts rotating. And then if we now somehow are able to maintain this rotating motion of the flywheel, and later on use that rotating motion and the kinetic energy due to the rotating motion and connect that to a generator, then we would be able to extract electricity out of it. Okay. Now, both the input and output to the flywheel, because we are using a motor or a generator, has to be in the form of AC or alternating current. If you want to have the final output in form of DC, or our input electricity is in the form of DC, we would need an inverter or a rectifier, as the case may be. Okay. So, this is essentially what a flywheel is. Okay. So, let us quickly write down some points on flywheel. As we know that I would write down something, that some of the points that we discussed. Flywheel stores energy in the form of kinetic energy, and this definitely is going to be during off peak hours. Right, and the stored energy is released to run a generator, and this is during peak hours. Clear? So, this is what we saw. All right. So, now if we want to do this, if you want to do some quick calculations. So, let us talk about, let us just draw this. I have an mg set, and of course, this is during off peak and the red is during peak. Okay. I would have some kind of a clutching mechanism, and then I have this flywheel. And this fellow is rotating. Okay. So, then what happens? What is the kinetic energy that is stored? If I write it as E k, it is going to be half I omega squared, where omega is the rotational speed, angular speed. What is its unit? Radians per second. Yeah. What is I? I is the moment of inertia. And for a rotating disc, it is going to be half m r squared. Clear? So, this is what I am showing here also in the flywheel calculations on the slide. As we can see here, we have the kinetic energy as half I omega squared, and for a cylinder, so for a solid cylinder or a disc, it is half m omega squared, where m is the mass of the flywheel. Okay. So, if you look at this, what are some of the points that we see directly? If we want to store a lot of energy, I can do it in two ways. One is by increasing the angular speed. Okay. So, therefore, E k is proportional to omega squared is proportional to I. So, if we need to store a lot of energy, we want high omega and we want high I. Clear? Now, for high omega, okay, that is good. So, if we need high omega, then what happens? The good thing is it goes as omega squared. However, we do not need, if we have a very bulky flywheel, it does not help. Okay. We would rather not have a very bulky flywheel, we would like to have it lightweight, but it shows here that if I have to increase the moment of inertia, I either need high mass or high radius, which means either a heavy material or a very large flywheel, which both of which go contrary to what we said, that we do not want a very bulky flywheel. So, what can we do? So, what we can do is, say this one I omega squared is for a disc or cylinder. Okay. However, if you imagine that instead of a solid disc, what I have is, an annular disc like the spokes of a cycle wheel, right. Most of the mass is concentrated along the circumference, and then we connect it to the hub by some thin members like the spokes of a cycle wheel, of the wheel of a bicycle, which is also similar to the the flywheel that was shown in the video that we just saw. You remember, it looked like something like this. So, most of the mass was concentrated on the periphery. There was of course a central hub, and then there were connecting rods like this. So, in this case I actually is m r squared, no half, all right. Okay. So, this is what it is. So, actually I is, as you recall from your mechanics, it is calculated as an integral over of the mass over the, I mean it is like r dm from 0 to r, and if you do that for this one, since most of the mass is located on the side, it becomes it comes out to be m r squared, clear. So, if we do this, then what happens? By without increasing the mass or the radius, I directly doubled my moment of inertia. Okay. So, I would say is then here go for construction or design with mass concentration on the outer periphery. It's possible? Okay. So, that is what I am saying, that you can increase. So, for storing higher energy, we increase omega or we increase the moment of inertia by locating more mass towards the circumference. All right. Now, what are the kind of omega or the angular speeds that we are talking about? If we talk about RPM, flywheels can easily rotate at RPMs of about 30,000, even 50,000. Actually, in some of the lab scale experiments, there has been demonstrations of running flywheel at even 100,000 RPM, very high. Okay. So, this is how flywheels operate and this is how it stores energy. So, what we typically do is we actually use materials with lighter mass and high tensile strength. For example, carbon fiber reinforced materials. Why? Lighter mass, as I said, we do not need it to be very bulky, because remember, from mechanical consideration you also have to hold this flywheel in place, make it rotate, you have to think about bearings and so on. So, a lightweight flywheel is always good. Okay. Even if your mass goes down a little bit, what we can do is we can concentrate that mass, as we just discussed in the previous bullets, we can concentrate it along the circumference and go for a higher angular speed, which I said is possible. Okay. Why is high tensile strength required? The high tensile strength is required because we are talking about very high RPM. So, there will be extremely high centrifugal force in the radial direction, and the material needs to be able to, or material needs to be strong enough to be able to withstand these high stresses. Okay. So, that is why the material that we used to construct a flywheel is important. Okay. What else is important? We will come to that. Before that, let us talk about some of these energy storage calculations, continue that. So, let us say the flywheel was running at initially at n1 and then accelerates to n2, and this is during the off peak hours. So, then what is the additional energy stored, right? It is half I omega 2 squared minus omega 1 squared, clear. Now, remember, what is omega? 2 pi n, n is revolutions per second or 2 pi f frequency. If it is RPM, if n is RPM, then it will be n by 60, but so n is revolutions per second, not RPM. Okay. So, if this is the case, and let us again consider I is half sorry, let us consider that high is mr squared. Okay. Again we are talking about this. So, what I will write is half m r squared, where we are using capital R or small r, no small r, sorry, okay, half m r squared, and then this will be 2 pi n 2 squared minus 2 pi n 1 squared. So, I can write it as 2 pi squared m r squared n 2 squared minus n 1 square. Okay. So, this is what I have written in the slide also. So, this is my energy stored when during peak off peak hours I rotate the flywheel and accelerate it from an angular speed of omega 1 to omega 2. Clear? Now, what happens? Then once I have energized it, I need to store this energy. Clear? But what are the problems? If I want to store it, which means the flywheel has to keep rotating and not slow down. Now, is that possible? It is not possible, because if I have it if I keep it rotating, then what happens is it is going to have air friction and it will slow down. There are also the mechanical bearings on which the flywheel rests, right. There is a shaft on to which it is attached and it is rotating. So, there will be some bearings, and this bearing will also have some losses. Okay. So, we are going to come to that. How do we minimize those? Okay. But before that, we also talked about the high tensile stresses that results because of this high speed rotation. So, as a result of that, we need to ensure that we need to ensure that the stress that is generated is less than the maximum tensile strength that the material can withstand. So, that is what is shown in the second equation over here, that if I look at the maximum energy density, which is energy stored per unit mass, is related to the maximum tensile strength in this form. So, the maximum energy that you can store per unit mass must be less than or equal to K, which is a constant and is a function of the material, sigma m, which is the maximum tensile strength of that material, over rho, which is the density of the material. Okay. This directly comes from solid mechanics. Okay. So, we need to make sure that this is what we need to satisfy. If we choose a material, this is what limits the maximum amount of energy that we can store. Otherwise, the material is going to disintegrate, because during the rotational motion it will not be able to withstand the tensile stresses. Okay. So, this is where the construction becomes important. The material, the spinning rotor, which is steel or carbon composite, carbon reinforced materials are used because they are strong and they are light. See, steel rotors can spin at around several thousand RPMs, but carbon composites can go up to 60,000 RPM. Clear? Let me take a little detour over here. When we talk of flywheel, one of the first applications that come to our mind is IC engines, right, as mechanical engineers. Well, the other place where flywheel is used, which these days we do not see in our houses that commonly, but when I was growing up it was probably common in every household, that was the sewing machine with a paddle. The sewing machine also uses a flywheel. Okay. So, that is a completely mechanical manual type that we saw. In IC engines, as mechanical engines, when we studied mechanical engineering, we came to know that the IC engine, the the cycle consists of 4 segments, 4 strokes. Okay. The suction stroke, the compression stroke, the expansion stroke, which we also call the power stroke, and then the exhaust stroke, 4 strokes. However, out of these 4, it is only the expansion or the power stroke that generates power. Okay. So, what happens during the other 3? So, that is where we use a flywheel. So, during the power stroke, the energy is supplied to the flywheel, which keeps it rotating, and during the other 3, that energy is extracted by the transmission system, and that is how when we ride we do not feel that, we feel it is a smooth ride, but actually the power is only given at during the power strokes. So, ideally we should have dung, 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 this kind of a motion, but that is what we do not see that, because it is the flywheel that absorbs the additional energy during the power stroke and then releases it during the other 3, so that we have a smooth ride. Okay. So, that was a little detour, but trying to understand how a flywheel works in terms of practical application. Here we are seeing a completely different application, which is energy storage. Well, IC engines is also energy storage, but here we are also seeing another example. And remember, flywheels cannot store a lot of energy, okay. But however, what it is done is it can use to stabilize a system, okay, when the it supplies that additional energy for a small amount of time, so that the system can run smoothly. Okay. All right. So, let us come back to the discussion here. We are talking about materials. So, steel rotors can spin at several thousand RPM, and the reason I take the detour is, if you have noticed during when you are driving a car, you have an odometer which shows the RPM. In many cars it is there. In the typical RPMs that we see, we restrict ourselves to 3000, 4000, that kind of RPM. Okay. Actually, even if you go beyond 2000 itself, the engine becomes a little noisy. It's quite so. I mean, normally safe drivers do not go beyond 2000, 2500 like that. Okay, we change the gear so that we do not go above. But however, the steel rotors in that is good enough. But if we really want to go to like 20,000 RPM, 30,000, 50,000, 60,000, then we need these more sophisticated, more strong materials, which are like carbon composites. All right. So, that was the material. Now, what about bearing? Okay. So, bearing, the mechanical bearings are not practical because there is friction, and the friction is proportional to speed. So, therefore, if you have mechanical bearings to support your flywheel, then we are going to lose that kinetic energy. Okay. So, that is why we cannot use mechanical energy. What we use is magnetic field, okay, magnetic bearings. So, one of the examples is magnetic, the magnetic levitation that we talked about. So, magnetic levitation is nowadays used, even we have trains running on magnetic levitation. Why? So that the friction is reduced. So, here also, if we want to use flywheels for high density storage systems, energy storage systems, and where we want to store the energy for a longer period of time, then what happens is we have to minimize friction. We cannot use mechanical bearings, we can use magnetic bearings where there is a magnetic field, okay, that supports the flywheel, okay. And there is also this, it's a little more involved, we are not going to go to the details, but there is also other opposing magnetic fields to hold it in place, because otherwise if you just have magnetic field in one direction, it may even fly away. But let us not get into those details. It is possible to have even magnetic levitation technology to hold the flywheel in place, and in that case there is hardly any bearing losses, okay. The other source of loss that I talked about was air friction. So, therefore, you can operate, we have to operate it in vacuum. Of course, perfect vacuum is never possible, but once the flywheel is housed in a chamber which is evacuated, so that air friction is very, very low, okay. How long can a flywheel retain its kinetic energy? Well, if you have magnetic bearings and if you can maintain close to vacuum conditions, it can keep running for almost 6 months. It has been shown, okay. So, the storage, the period of storage probably can be quite large if we use flywheels for energy storage, okay. Now, the last thing that I want to mention, however, is that what if it fails? Okay. What if it fails? We have talked about special materials that can withstand high tensile strength, with high tensile strength, etc. All that is fine. But what if it fails? Because we are talking about something that is rotating at extremely high speed. Okay. So the good thing is that the design is such that, or the material construction and design, and I am not getting into the details, but it suffices to know that the construction is such that if the material fails, if it breaks or cracks, it immediately disintegrates into small pieces. So you really do not have a large chunk coming out at very high speed, which if it hits something can be fatal at those high speeds. So what it does is it immediately disintegrates into small pieces, and then you also have the housing, so that these pieces, when it goes and bangs against the housing wall, the force is not strong enough because the mass is small, and that is how we keep it safe. All right. So once again, we started by discussing what is a flywheel. So flywheel is a rotating member which can be rotated and accelerated, or basically the angular speed can be increased by supplying additional energy, and this we do during off peak hours when we have additional electricity generation. So we use it to run a motor that supplies energy to the flywheel. So kinetic energy goes up because its angular speed goes up. Then what happens once it has reached a certain RPM, which will be dictated by the material's tensile strength, and therefore what is the maximum angular speed it can have for a given design, we will stop supplying additional power through the motor. The flywheel is housed in a casing which is typically evacuated so that air friction is minimized. Also the bearings are special, typically magnetic bearings, so that the bearing losses are also minimal. So in this scenario, when it is rotating at certain RPM, it can keep rotating, okay, with minimal loss of energy or RPM. Next what happens is, during peak hours when I need this additional electricity, I attach the shaft of a generator to this flywheel, and so therefore what happens is, the kinetic energy of the flywheel is used to rotate the generator and thus produce electricity. Of course, as it rotates the generator, its speed is going to come down, so the RPM is going to fall from that omega 2 to some lower value, let us say finally to omega 1 or even lower, we do not know, and but that is how we generate, that is the amount of energy that will be released. All right. So the flywheels typically are not used for very high amount of energy storage, but it can supply high power in short bursts, and therefore it is typically used to stabilize the system and supply that additional burst of energy for a small period of time. Okay. We also talked about its construction in the sense that we typically do not have a solid disc or a cylinder, but instead go for a construction where the mass is concentrated on the outer periphery. So that way what happens is, we can have higher moment of inertia because it goes as mr squared instead of half mr squared in case when the cylinder or the disc is solid. Okay. And the other thing, from design point of view, we would like to have a lighter mass because that is easier, especially when you are talking about magnetic field. It will be easier to hold the flywheel in its place with a magnetic field strength of lesser intensity because the mass is lower, and we would like to compensate and have high energy storage by increasing its RPM, because today's technology enables us to go to really high RPMs in flywheels. Okay. Last but not the least, the design is such that if it fails, it disintegrates into small pieces, so that we do not really have very hazardous condition. We do not have large chunks of a material at such high speed flying around. All right. So that kind of wraps up our discussion on flywheel, and in the next class what we will do is we will look at another means of energy storage. Thank you very much.